We're back. It's been a while. We're back though. Today's lesson is a new module, but it's chapter 5. We're talking about text embeddings. And I know we've talked about this in the first chapter about what text embeddings are, how AI is able to really store and understand what words are, right? How to interpret words and sentences. So in this module, we're going to take a visual approach to gain that intuition behind those text embeddings, what use cases they're used for, and how they can be customized using fine tuning. So we previously learned about what text embedding is as a whole, and now we're going to go into how we can use that to really tweak the model so that the model can understand and do things that we want it to do. In this example, we're going to be using Cohere's Python Software Development Kit, or SDK, but don't worry, we're not going to be going into the code too much. We're just going to go through what that would look like. I think that's a key part to understanding how these LLMs operate, is just looking at the code. We don't really need to run it, but we need to understand what's going on within it. So when you hear about large language models, or LLMs, the first thing that comes to mind might be the ability to have this text generation, right? When you go to ChatGPT and you ask it a question, it brings back or it generates this new text, right? So it could be an essay, it could be a paragraph, it could even be a marketing copy. And another thing you can get is text representation, or a set of numbers that represents what the text means and captures the semantics of the text. So these numbers are called text embeddings. So not only do you have the text generation, or the return of those paragraphs and phrases, but also within that text generation, you have the text representation, or how the LLM is interpreting each word in a sentence, in a paragraph, or a sentence in a paragraph. And so text generation outputs text, while text generation outputs text, while text representation outputs embeddings. So again, the top one here, text generation, is going to output the text, what we're familiar with, what we see when we go to ChatGPT and we type in a question, hey, how old is the Miami Heat? And it would provide a response. Whereas text representation would look at how old is the heat and be able to decide what we're referring to when we say heat. Are we talking about fire? Are we talking about peppers? What heat in this context? Is the H capital, right? And so even when we're not doing things like that, when we're not providing context such as a capital H, if everything was lowercase, right, this LLM would have to be able to decide and understand what we're talking about, and that is where those embeddings come in. And so text embeddings give the ability to return this unstructured text data. To us, it's structured, right? In our heads, we're talking it. To us, it makes sense. But to the LLM, it doesn't understand any of this. It doesn't know what that means. And so with embeddings, you can compare two or more pieces of text, be it a single word, or sentences to sentences, or paragraphs, or even entire documents. And since these are basically broken down into numbers, the ways you can process and extract insights from these sentences, from these paragraphs, are only limited by our imagination. So you might have heard me talk about previously that these LLMs, because they're able to break down text, words, paragraphs into numbers, they may be able to make associations between these words, these sentences, that humans might not other be able to make, right? Because we don't store words and phrases as numbers. We store them as is, and we try to recall them from what we remember, and that's where we run into these hard moments of what was her name, or what did they mean by that, right? We can't really conceptualize things as fast or as easy as an LLM would be if they're converting everything to numbers. But what does this bring, right? What does converting these to numbers bring? Is that it opens up many possibility use cases that apply in the real world, right? Embeddings power applications we interact with on a daily basis, such as even search engines, right? They embed, or they remember what people are typing in. E-commerce product recommendations, right? They might see how certain customers are buying certain products, or how likely or more likely they are to buy certain products, or social media content moderation, right? When someone says a certain word or phrase, what do they mean by that? Is that legit for this site? Is that good enough? And so forth. And so in this chapter, we're going to take a visual approach to understand the intuition, right? How are these text embeddings happening, and why are they happening? here we have this, oh, we're frozen again. We are frozen. All right, there we go. So this is how we're going to begin this LLM training, right? This is how we're going to begin those text embeddings. And so that right at the start, we can see we're importing a few libraries: Pandas, NumPy, Altair. So this is Python here. But then at the bottom, we see we're importing some more libraries, or some more sections of libraries, and we can see this PCA, cosine similarity, and k-means. Well, k-means is a way of grouping. So right there, we have a way of clustering the data. And cosine similarity, as we recall before, is a way for us to make sense, or a way for the LLM to make sense of when a word is used and it has multiple meanings, how similar are these words, right? Even other words that have nothing to do with one another, how similar are they based on the angle between the words? And then the second import we're doing there is we're importing Cohere, right? The LLM itself. And here you see that they provide an API key to use the Cohere model. But again, we're not running any of this. We're just going through what that would look like. So the first step that they have us doing is we're using a data set, a subset of the entire airline travel information system intent classification data set. I don't really have an idea of what that is, but let's open this up and see what that might be. So the ATIS dataset is a standard benchmark dataset widely used as an intent classification. ATIS stands for Airline Travel Information System. What we do know is that this dataset provides large numbers of messages and their associated intents that can be used in training a classifier. Within a chatbot, intent refers to the goal the customer has in mind when typing in a question or comment. So while entity refers to the modifier the customers use to describe their issue, the intent is what they really mean. And for example, a user says, "I need new shoes." The intent behind the message is to browse the footwear on offer. Understanding the intent of the customer is key to implementing a successful chatbot experience for end user. So another example of this would be, someone going to even Google and typing in, best restaurants in my area, right? They're not asking best restaurants because they want to look at best restaurants or just understand the best restaurants. And that might be some instances, but most instances they're looking up the best restaurants because they want to eat at these restaurants. And the time of day might matter, right? You're not going to eat dinner for breakfast if they're looking at breakfast. And so all of this context, all of this data, right, has to be put into context for the LLM to understand and respond, right? The same way that humans try to understand the questions that are being asked them so they can respond appropriately. So the first step in this code, we are loading the data set to a data frame. Basically, we're just loading this into code, or a way for the code, for the LLM to understand the data, right? We're reading the CSV file and we're importing it into this Python code, essentially. Then we're going to take a small sample from the code. And so we're making a sample class of airfare, airline, and ground service. And then we're basically having the code put these into those specific classes of, is it an airline, is it airfare, or is it ground service? And then we're removing unnecessary columns, which would be, the intent column. So here are a few examples of what we're importing, right? Which airlines fly from Boston to Washington, D.C. via other cities? Show me the airlines that fly between Toronto and Denver. Show me round trip first class tickets from New York to Miami. And so we can see all of these are things that are in this ATIS data set, right? They all have everything to do with airlines. And what we are doing is we're trying to put these individual sentences, or these phrases, basically bucket them and help cluster them into which one has to do with airline, or which one has airlines in it, which one has airfare in it, which one has ground service in it. So once we've done that, we then want to turn these into those text embeddings. So next we embed each inquiry by calling the Cohere's embed endpoint, which is co.embed. It takes in text as input and returns embeddings as output. And so in this instance, we are going to supply 3 parameters, right? Text, which is the list of text you want to embed. Model, the model to use to generate the embeddings. At the time of writing, there are 4 models available. We can see that they're all English, English, and then 2 multilingual, and then the third parameter being the input type. So this is going to specify the type of document to embed. And so at the time of writing, there are 4 options here as well. We have a search document where we can search the document or documents against which search is performed, smart search like Google. We have query to query the document. So if instead you wanted to use something to basically, write like Notebook LM to look through these documents or to summarize the documents. We have classification for when the embeddings will be used as an input to a text classifier, right? For when these embeddings are going to be used to identify, right, how close these words are to one another, or clustering for when we want to cluster them or make sense of words that are in similar veins in similar areas. So we can see the code here of them defining how to get those embeddings and what that might look like. So they're defining the variable get embeddings, and then at the bottom here we are saying, hey, we're going to use query embeds to get embeddings, and up here we see what get embeddings is, and this is what that entire thing looks like. And so for every piece of text that's passed to the embed endpoint, a sequence of 1024 numbers will be generated against for a phrase, for the sentence, for whatever it may be. And again, this is common practice to have these many points, but because the AIs can process and store so much data, because these models have been trained on so much data, they're going to have a lot of embedding points, more than humans may even be able to comprehend what those may be. And so here at the bottom are the first few dimensions that this embedding algorithm, or this embed English v3 has done for us. For show me a list of ground transportation at Boston Airport, which we recall is in our ATIS data set at the top, right? Show me a list of ground transportation at Boston Airport. And then we can see here, these are the text embeddings that will return, or at least a few of them. And so once we have the embeddings for our phrases, for our words, for this ATIS data set, we want to visualize them, right? We want to get some visual intuition about this by plotting these numbers in a heat map. And what we can do is we can compress the dimension to a much lower number. So instead of 1024 different numbers, we're just going to use 10. And these 10, while we may not be specifying it here, these 10 could be things that we understand as humans. It could be, okay, which one has, again, airline, which one is Boston, which one's ground, and so forth, right? And so the get PC function below, which we see here, does this via a change or a technique called principal component analysis, which reduces the number of dimensions in an embedding while retaining as much information as possible, right? So just as like I said, a human might go through and pick the columns that make the most sense, what this function is going to do is it's going to go through and say, okay, which of these columns even looks remotely impactful, right? Which one of these embedding points should we use, or that has the most information regarding these embeddings? And so we set embeds PC to the 10-dimensional version of the document embedding. So again, instead of 1024, we're only going to return 10. They're saying we'll use the 9 data points above as examples and display their compressed embeddings on a heat map. Again, those 9 data points are going to be those texts that we saw from the ATIS document here. And so once we put that onto a heat map, we have each data point on the y-axis and its corresponding set of 10 embedding values on the x-axis, right? So on the left-hand side, you can see those phrases, and then on the bottom here, you can see their embedding, right? So the embedding 0, what's that heat map look like? What's that value look like? So heat map showing 10-dimensional embeddings of 9 data points is what we have. There are some patterns emerging. If you can look at this and you can see, wow, there's some darker colors on the left-hand side. And as we move to the right, that value becomes a little bit less, right? And so to see this, let's look at an even smaller number of examples. So instead of all 9 of these, we're going to look at 3. And if we take these 3 examples, we can see that they're all inquiries about ground transportation in Boston, right? If we read them, show me a list of ground transportation at Boston Airport, show me Boston ground transportation, what ground transportation available at in Boston. So we can see they're all surrounding ground transportation. And by visual inspection, we can see that their embedding patterns are very similar. On the left-hand side, they all are dark. On the right-hand side, they're all light and somewhat of a mix in between. The 10-dimensional embeddings of 3 inquiries all about ground transportation in Boston should look very similar. in some regard. So now if we compare them to other kinds of inquiries, such as those related to airline information, which are the two below, we may notice that while the embeddings about ground transportation inquiries look very similar to each other, they are distinctive from the rest, right? We can see these two, which are about airlines, don't have that darkness on the left, but it's rather in the middle where the above phrases don't have anything like that. And so here the model was able to capture the context and meaning of each piece of text and then represents them as embeddings. Each dimension of an embedding called a feature, so each dimension of an embedding, those numbers themselves are called features, represent a certain universal characteristic of text according to how the model understands it. How is this possible? Well, a large language model has been pre-trained with a vast amount of text data, typically we can even say all the data on the internet, but in this case we can liken that to, imagine if Google, right, their Gemini, they were just training this on everything that passed through Google search, right? They have access to that. Or Twitter, I believe it's Grok, right? Elon Musk, they're training it on all the Twitter data, which is a good way to see how people would communicate with one another, albeit a little bit skewed because people are more vocal on these social media platforms. And so a large language model, right, has been pre-trained on this vast amount of data, and where the training objective is set up in such a way as to encourage the model to extract contextual information about a piece of text and store it as embeddings. So again, it's been trained on all of this data to learn and be able to understand how to turn these words, these phrases, these sentences into embeddings, and then how and where to store those embeddings. And so let's then visualize what these embeddings look like on a 2D plot or just a graph, right? The spatial awareness of where these embeddings sit. And so for embedding these as sentences, we can investigate this further by compressing the embeddings to 2 dimensions and plotting them on the scatter plot. And what we would expect is that the texts of similar meaning would be closer to each other and vice versa. So the ground transportations ones would sort of cluster together. The airline ones would sort of be together or closer together, right? They all have different words. They might be referring to different cities or different airlines, but they're going to be relatively closer than they would otherwise be to the other phrases. And so do note that as we compare the embeddings to lower dimensions, the information retained becomes lesser. However, humans can only visualize in 2D or 3D, and it turns out that this is still a good enough approximation to help us gain intuition about the data, right? And this begs into question, are these LLMs even limited by 2D and 3-dimensional shapes, right? Because we created them in the world that we know, are they then able to plot these on even 10-dimensional shapes or 1024-dimensional shapes on how to best represent the data so that they can go grab it? So by visual inspection of this graph, we can see, or the scatter plot, we can see that the texts of similar meaning are indeed located close together, right? On the right-hand side, you can see ground transportation, on the left, tickets, and so forth. And so we see inquiries about tickets clustered with tickets, ground clustered with ground. And these kind of insights enable various downstream analyses and applications, such as topic modeling and clustering, such as in documents, right? If you have a bunch of documents, how would it know which document should go where? And in other words, text embeddings allow us to take a huge corpus of unstructured text and turn it into structured form, making it possible to objectively compare, dissect, and derive insights from all the text in a document. And so what we've concluded here is that embedding is one of the key focal points of how LLMs operate, right? Text embeddings make possible a wide array of downstream applications such as semantic search, clustering, and classification. And so if we scroll up, again, what this is going to be able to help us do once we have those embeddings, once that text is embedded, right? Once we have those embeddings and those data points, we can then generate that text to respond to the prompt, to the query that the LLM is being asked. There is one thing, now that this is done, that I do want to show, which is something that happened very recently about AI. It was on Bankless, but it was I don't see it here, but one of the things that has happened recently is that someone has created an AI agent, an AI bot, to go out and be able to purchase pizza, right? Just as much as Bitcoin was used to purchase pizza in its first major transaction. An AI agent was able to autonomously go out on its own and purchase pizza. The only thing it was prompted to do was go get pizza. It decided on itself to download a crypto wallet, to create a crypto wallet, get crypto, and use that to purchase a pizza. Now, all of this on the surface might sound pretty cool, but there's a lot going on here. This agent, it was able to dissect what this prompt was, what this meaning was via its embeddings. Okay, it wants me to go find a way to purchase pizza. And it did everything necessary to be able to do that, right? How would it be able to get money to purchase pizza? How would it be able to communicate? It actually was a vocal AI as well, so it was able to explain everything that it was doing along the way to the developers. Hey, call the pizza place, which I'm not sure that it did. We can assume that it just purchased it online where there was no vocal exchange needed, but all of these steps took place to the pizza order was delivered. And with this use case, what we're outlining is that these AI agents are going to be able to talk to one another. So imagine on the other end of this pizza line, of this pizza place, there was another AI agent that was tasked with making pizza. And so when you have these agentic AIs, you can start to see how they can communicate with one another to create end results, right? This AI to go get pizza might be confined in its local computer, right? It might be confined in the developer's computer, but if the AI on the other end at the pizza place was a robot that had specific parameters of, hey, ingest pizza orders and go make the pizzas, that's all they're responsible for, you can start to see how these agentic AIs can start to work with one another to build things out. All right, we are at time here. Happy Friday, 8:40. Thanks for joining another episode of Pear Does. Deuces.